do need to be familiar with what these forces are, where they come from. So if you look at an individual structure, it's boom, it's that bond, it's going to have that force, that means this type of reaction. Okay. The reaction part you don't need to stress as much about at this point. When we push a little bit more into chapter 2, when we look at classifying reactions, acids and bases, that's when you're going to need to start applying that a little bit more. Okay? So you need to be familiar with those forces and kind of what they end up doing. The primary one that you're going to be concerned about is this solubility concept, and in particular solubility in water. Why? Why is hydrogen bonding important? It's not everything. Our solvent for all biochemistry is water. So what we're really concerned about is our biomolecules dissolving in water, so their solubilities. Right? So if we're looking at solubility, our rule of thumb is like dissolves like, which we can tweak a little bit into like forces dissolve like forces. So if we look at the structure of water, okay, we've got our standard H2O, and we can look at our molecule, and within that molecule we see bonds. What bonds are present in water? Careful. Polar covalent bonds. So our bonds are just these three options: ionic, polar covalent, and covalent. So we have polar covalent bonds, which I'm just going to abbreviate as PC, okay, which means what type of force? Okay, and from this curve, if we've got a polar covalent bond, that translates directly across color-wise over into a dipole-dipole force. If you have a dipole-dipole force, then you can evaluate if there's hydrogen bonding. Okay? Because hydrogen bonding is specifically a type of dipole-dipole. If you do not have a dipole-dipole, you do not have hydrogen bonding, period. Okay? How do we get a dipole-dipole force? We have to have a difference in electronegativity, positives and negatives. Once we've got that strong difference in electronegativity, then we can look for our second follow-up for hydrogen bonding, which is we have to have a hydrogen bound to nitrogen, oxygen, or I already forgot which ones did I say, nitrogen, oxygen, or fluorine. Okay. Is fluorine going to be particularly relevant? Probably not. It just doesn't show up very commonly in biological molecules, so we don't need to stress as much about fluorine. Okay. So with hydrogen bonding, or with water, we've got hydrogen bonding as a force. If we're going to look at solubility, what force would we expect to see for a compound to be soluble in water? What force? Okay, dipole-dipoles are a possibility. Remember, our rule of thumb is like dissolves like. What's the primary force we would expect to see? Hydrogen bonding. That is the identical force. Okay? So if we see hydrogen bonding, it is very likely that our compound becomes soluble. Okay? There are, of course, exceptions to that. Okay? For instance, if we take a look at this compound, which I'm going to switch to an abbreviation here in a second, we have what compound in the lower right?
Ethanol.
It's ethanol. What's the solubility of ethanol in water? Really, really, really high. Okay, they are completely miscible. How do we know that? Well, what's in beer? Water and ethanol. What's in any hard alcohol? Water and ethanol. They are extremely soluble with each other. Okay? So we see that hydrogen bonding, so yeah, we say soluble. But what happens if instead of that being just two carbons, we string this out to a whole bunch more carbons? It still has hydrogen bonding, okay, but does that big long carbon chain affect the solubility? Okay. It has a significant effect. Most of this structure now is just carbons and hydrogens. Well, what kind of bond do we have between carbon and hydrogen? Non-polar covalent, which gives us London dispersion forces. What's the similarity between hydrogen bonding and London dispersion? Virtually no similarity, which means we're now at a debate. We have London dispersion versus hydrogen bonding. Which one wins out? London dispersion in this case. So there's a gray area on deciding between it. Okay? The general, again, approximate rule of thumb is for a single hydrogen bonding type OH or NH situation, 4 carbons. Anything more than 4 carbons after that single interaction, it becomes insoluble. Okay? London dispersion dominates. Okay? So could we ask the question, or could I ask the question, I guess, on an exam? What's the solubility now of this compound?
In water.
In water. Okay, well, it's exactly at 4 carbons. That's a bit of a tricky question. There's no way I would ask that question. Okay, what we're looking at is the larger kind of polarizing black and white differences. But remember, everything is a spectrum through these. We're looking at when do those interactions dominate, when do they not dominate. Okay? For the most part in biochem, we're not concerned about the gray areas. We get very black and white differences. So you wouldn't be asked this question because butanol doesn't show up as a common organic compound in biochemistry. That larger structure that we just drew up, that whatever that was, dodecanol, we can see equivalents to that, but we typically don't even see that alcohol either.
You mentioned earlier, I think it was the first class, methanol doesn't have this solubility, and that's why it's so problematic?
Methanol has a very high solubility. Yeah. It's not so much the solubility in that case, it's the reactivity of each of the precursors to excreting that compound.
Okay, I didn't want to confuse
Yeah, and so you get 2 different parallels. Because biochem is infinitely complex, you can look at it at all sorts of different levels. We could look at it as a solubility level, but then each of those molecules can potentially react with something within our biological system. That reaction can lead to side effects.
When we see a long chain of carbons like that, can we just think lipids and think that it won't?
You can jump to the biological term for it, which would be our lipids. Yeah, which unfortunately didn't show up in chapter 1, but if you take a look, search through the textbook for lipids, there's a full section on it where they show primarily just carbon structures. Right. So yeah, thinking lipids or insoluble in water is going to be your best bet. After that, we can push into reactivity. You get this Bronsted-Lowry acid-base stuff, and if you remember from your OChem, we also have Lewis acid-base and electrophile nucleophiles. Okay? Lewis acids and bases are really the parent to everything, so everything can be classified as a Lewis acid or base. We can subcategorize into Bronsted-Lowry acid-base definitions, and we can subcategorize into electrophile nucleophiles. In the Bronsted-Lowry acid-base definition, what changes? What are we looking at? Acceptor and donor of Bronsted-Lowry is protons.
Yeah, bases and protons.
Okay, so we're looking at H+, hydrogen ions. Our acid is a donor. Should have given more space here. I have a feeling it shows up with more space later. And our base is an acceptor. When we move to electrophiles and nucleophiles, still acceptors and donors, except now what we're looking at, electrons. Okay. So your electrophile is electron loving, so it is an electron acceptor. A nucleophile is an electron. That is very excited next door. An electron donor. Okay. In OChem, you were asked to go through and classify pretty much all of your reactions based on those 2 systems and a balance between those. When we move into biochem, biochemists are notoriously incapable of understanding organic chemistry. That was a bit harsh. And what we switch to instead is kind of a simple version. We just look at the Bronsted-Lowry acid-base definition. We can still apply, and we will still apply, the nucleophile electrophile concept much later in the semester, but our primary focus for almost everything we want to work with is in the Bronsted-Lowry definition, which means you absolutely need to know those definitions. Okay? And you will need to apply them for individual structures that you encounter. Okay? Things to watch out for when we're looking at these interactions. Okay? If what we just talked about was identifying bond type, then coming up with a force type, and then classifying our molecule accordingly. Okay? So the example that I gave in the organic class just the other day is if we look at this compound, or partial bond. We might look at this and say that this is a polar covalent bond, so we have a partial negative on our oxygen because it's more electronegative than carbon, and our carbon is a partial positive. We might say this molecule is relatively reactive because of these partial charges. Okay? So those charges allow us to see those interactions. But what happens if we extend the structure out to, say, this compound? We still have another partial negative over here. So we might say, oh, even more reactive because we have more charges. What ends up happening? They cancel, and the molecule ends up becoming, for all intents and purposes, almost neutral, and we don't really see a large buildup of charge through the molecule, which means we don't get a lot of interactions with this compound with other species. Is this something that we know to be true already? Well, if we look at the global warming conversation, one of the molecules involved with global warming is CO2. Okay? If CO2 was incredibly reactive, okay, it wouldn't be an issue with global warming because it would have disappeared. It would not be CO2 anymore. Okay? It is very, very hard to get a molecule of CO2 to react. Okay? Because of that, it sits in our atmosphere and it can affect our warming environments. Okay? So we have to look beyond just the bond. We have to look at the molecule and ultimately the shape of the molecule. What defines our shape? That's where we run into the valence shell electron pair repulsion theory, all that fun stuff, their tetrahedrals, trigonal pyramidals, bents, all that fun jazz. Okay? It is important to keep that kind of in the back of your head. It's not going to be important to use, particularly throughout the whole semester. I'll probably reference it every so often, but it's kind of a minimal effect. Okay? Primarily what we're going to be looking at is that our tetrahedral shape applies to carbon, okay, which means we've got a molecule that's very, very symmetrical. So in most cases when we see carbon, it kind of neutralizes its overall charge if we're in that shape. If we move to trigonal pyramidal, we're looking at what atom? Nitrogen. Nitrogen tends to be a polar molecule. Why? If we look at the shape, one end of it has a pair of lone pairs. The other end has a bunch of atoms. So we have a polarity associated with this. Carbon, throughout as a rough approximation, is relatively neutral. What's the reactivity of our nitrogen? Nitrogen is more reactive and it typically acts as a base. It will donate its electrons, okay, or pick up a hydrogen. If we move to oxygen, the last one, oxygen's kind of in a weird spot, can really act as both. Okay, but we primarily see it acting as an acid. Well, actually, no, both is a better term, but we see that acid characteristic start to build up. If we look at our periodic table, why does this kind of make sense? Well, carbon, we said, starts neutral. Then what happens? As we move further to the right, we add in an extra lone pair. Nitrogen now has a lone pair that it can potentially donate. What else changes as we move from left to right? Electronegativity. Okay? Nitrogen is more electronegative than our carbon, not quite electronegative enough to take electrons away from a hydrogen bound to it. So if we drop a hydrogen in there, it doesn't quite have enough electronegativity to take the electrons away from the hydrogen. If it can't take electrons away from a hydrogen bound to it, what happens? Can it act as an acid? So if we draw that bond, we're saying nitrogen is not electronegative enough to take the electrons away from the hydrogen, which means the hydrogen stays bound, which means can the nitrogen donate a hydrogen? No. If it can't donate the hydrogen, it can't act as an acid. So then the only thing left is to look at what can happen as a base. Well, to act as a base, it has to have electrons to share with a hydrogen. Does it have electrons? Yes. Okay. As we continue to move across our periodic table, we run into oxygen. Okay. Oxygen is much more electronegative. So now it starts to be strong enough where it can take the electrons away from a bound hydrogen, which means an OH bond can be acidic. It can act as an acid. So we get that option. We still have these lone pairs. Okay? Those lone pairs can still act as electron donors or proton acceptors. So we get both characteristics happening there. As we take one more step further across, we run into our halogens. When we put a hydrogen on a halogen, what happens? Or actually, any of our halogens. How do our halogens react typically? Are they good bases? No, they're pretty horrible bases. We look at chlorine, bromine, and iodine. We add a hydrogen to it, what do we get? A strong acid. Okay? Strong acids, the conjugate base is by definition really, really weak. Okay? Which means we don't have bases with those. Fluorine's kind of a weird exception. We don't need to worry too much about that. Okay? So if they can't act as a base, when we add a hydrogen to them, what do they then act as? Well, you already said that. They act as strong acids. So as we move across, we move from pretty much no reactivity to now basic, to now anything to acidic. Okay? And if we can keep that general trend in mind, that can help us go through and apply these. Okay? Just like with organic chemistry, we're primarily concerned about just that second row. It gets a little bit easier in biochem because we really just focus on carbon, nitrogen, oxygen. Okay? Halogens don't show up all that much, and occasionally we'll see phosphorus and sulfur, but if we remember how our nitrogen and oxygen react, the phosphorus and sulfur kind of follow suit. Okay? So we can look at solubility for each of these compounds. We started to address some of these issues. So if we take a look at salt, a salt structure would be NaCl, right? My standard salt. What intermolecular force would we get for that? We get the ionic force. If we take a look at water, water had what force?
I thought ionic was a type of bond.
It's both.
Okay.
Yeah, we got to be careful.
Yeah.
We go, I'm about to delete everything I just wrote. Oh well. If we go back and look at the top there, ionic crosses the bridge. You get both bonds and forces.
Yeah.
Sometimes you'll see a textbook refer to the force where it's ionic as electrostatic. Or they try and drop it as an ion force, try and kind of hide their name from it. It's one of the reasons why the ionic force/bond becomes exceptionally tricky for people to understand. Okay. So if we go through, we got our sodium chloride, which we said was ionic, or electrostatic, but that's too long of a word, so help me why no one uses it, and H2O, which we said was hydrogen bonding. Solubility, what do we think? Okay. We got a couple answers that could float out here. I heard a no. The no was possibly coming from hydrogen bonding is not the same as ionic. Okay. And the yes is probably coming from the understanding of the solubility of salt and water, which is very, very high. Okay. Water will dissolve most polar compounds. So it will dissolve some compounds that are dipole-dipole forces. Well, if it dissolves the lower force, what's it going to do with the higher force? Probably also dissolve that one. The reason why that works, or why it can disrupt the really strong ionic force, is not because we're generating a single interaction. Let me clear all that. So when we look at sodium chloride and water, it dissociates into its ions. And if we look at the strength of the attraction between there versus the strength of the attraction with water, okay, and this is where things get kind of interesting. For it to dissolve, our purple attraction must be stronger than our blue attraction. Okay, we have to break that blue attraction to actually get it to dissolve, otherwise it's not going to dissolve. So if we go through and look at this, we're looking at an ionic force versus a really strong hydrogen bonding force. Which is stronger, ionic or really strong hydrogen bonding? Ionic. That's a bit of a problem. Our theory then says that that should not dissolve. Okay? But when we shift into a solvent or aqueous environment, are we looking at a single interaction between our molecule and our solvent? No, we're looking at a lot of interactions. And what we end up with is a solvent sphere. Okay. So we'll look at the sum total of all our water molecules interacting with a single sodium versus the single ionic interaction. All of the water molecule strength, even though they're individually a weaker interaction, in sum total are stronger. So this is why when we look at our ionic compounds, they are almost always water soluble. So if you see an ion show up in a compound, water soluble. Okay. Are there exceptions? Absolutely. Biochemistry is full of exceptions to this. What we're looking at is general trends. Okay.
Well,
Yeah.
and then you look at saturation point too.
You can look at saturation point. That's going to bring in a lot more math and graphs than I really want to deal with. There's better places to look at the math and graphs. But yes, saturation becomes important.
If this is too in depth, shoot me down, but does that sodium ion need a certain electron configuration to interact with each individual oxygen, or is this just a
That's
general force?
too
that
in-depth.
pulls it
So
out?
your electron configuration, first off, when we think of electron configuration, we think these locked things.
Yeah,
That's not true when we get into atoms. It's not locked thing. It's our electrons are constantly moving around the structure. So it's not it has to be in this configuration. It's in all possible configurations at all possible times. So we don't have to worry about that by making that kind of wishy-washy statement.
yeah.
If we go through and take a look at salt dissolving in water, we can come up with an explanation. If we go through and look at oil, our structure for most oils, right, is just carbons and hydrogens. Let's just draw methane as an example. If we go through and look at this interaction, we've got our red interaction versus our purple. Okay, why do we not expect methane to dissolve in water? We're looking at a highly polar molecule with a nonpolar molecule. That interaction should be actually relatively strong. That's much stronger than this. Absolutely is. But why does it not dissolve then?
The carbon is not going to let go of its hydrogen.
We're not talking about breaking any bonds. We're just saying the interaction. So that
So
dotted
it's not gonna
line
be
between the
attracted.
oxygen and the hydrogen. So it's going to have a weak attraction, but it is a stronger attraction than this hydrogen to that hydrogen, because those have no dipoles. Here we do have at least some dipole. So why does this compound not dissolve in water? If the interactions with water are stronger than the interactions between our nonpolar compound.
Because oxygen is
Carbon
wanting
doesn't
more
want to be a
electrons.
carbocation.
No, you're breaking bonds to do that.
Oxygen is wanting more electrons?
No. What we just looked at in both these cases was our solute dissolved in the solvent, and then how the solute interacted with itself. So there's the solute-solute interaction, there's the solute-solvent interaction, and solvent-solvent interaction. To dissociate, water must also break its hydrogen bonding interactions. Okay. In the case of the salt, we end up generating a really strong interaction there because one of those pieces was an ion. Okay, so the interaction is actually stronger in the solute-solvent situation than it was in the solvent-solvent. When we move to this case, the interaction here is stronger than our solute-solute. But what is it in comparison to our solvent?
It's
Much, much weaker. So what does water decide to do as a choice? It stays in its solvent interaction, so it can neutralize its own charges. The solute does not do anything to help stabilize those charges. So what ends up happening? No solubility. We get very weak interactions, and we get layers separating these things out. So when we think about dirt, okay, or oils that we get on our skin, we want to try and wash those things off. Okay, we don't want them on our skin. So how do we get them off? Okay, one of the common things is just try water, but water doesn't work. Okay, particularly if we have particularly oily or greasy things. So we add soap. Well, what is soap doing?
dissociate.
Encapsulating the oil.
all of those are sort of appropriate terms. We take a look at the structure of soap. Those are all supposed to represent carbons and hydrogens. At one end of our soap molecule, what do we have? It's not a carboxylic acid.
Resonance.
There's resonance, but we're still too complex. All these arrows that are hopefully being shown up there. We have a charge, so ultimately we have an ion. We have an ionic compound. What do ionic compounds do? They dissolve in water. So we now have a compound that should be soluble in water. Okay? But if it's soluble in water, that's probably not going to interact with the dirt for the very same reason that our water didn't interact with the dirt or grease. What's the other end of the molecule? We're looking at just carbon hydrogen, so we have nonpolar covalent bonds, which leads to what type of force? London dispersion forces, or LDF forces. Well, that end is not soluble in water. So what ends up happening is there's a balance with our soap molecule. Part of it stays dissolved in water, part of it does not, which becomes very helpful when we're trying to get grease off, because the grease then interacts with the nonpolar part of our soap molecule, and then the polar part helps kind of hold it attached to the water, so that when we run water over our hands, after rubbing soap all over it, what happens? The grease and the soap all gets washed off. Okay? If that was all that was happening, that would be kind of nice. It usually shifts into a larger picture, and what we're forming are things called micelles, okay? Where we have a polar head group. So all the white sections are your polar head group, and we have all those orange sections on the inside, which are our nonpolar tails. And they have to be tails. They can't just be a short 1 or 2 carbon chain, because if it's only 1 to 2 carbons, then our molecule on its own is completely soluble in water. We need a long enough chain that it can interact with the dirt molecules, the oil molecules. What is a long enough chain? It depends on what you're trying to do, okay, and what you're trying to dissolve. So different soap molecules will have different properties. Biology takes advantage of this same process, because what we want to do is, in a world of water, if I want a cell to exist within an individual solution and be separate from every other cell, there has to be some dividing line. But if cells are almost all water, and our water is all water, what's the dividing line? Everything's soluble. Okay? So what did cells, for whatever reason, generate? Well, it took advantage of these nonpolar molecules like soap, and they generated a barrier. Okay? We can have a micelle where we just have a nonpolar section in the middle, and then we can say all life is nonpolar. But if it's nonpolar, what's the likelihood anything's going to react with itself? Very little. We need that polarity to do a reaction. But we also need to separate that material, that genetic material, from everything else. Okay, so you need some way to define it. That's where you end up with what we can refer to in smaller cases as a liposome, where we have a polar head group on the outside, so the molecule can still move through water. And then we've got another layer of those molecules on the inside, so that the inside is now polar as well. So now the inside can do all sorts of crazy interactions it wants to within water. And we now have a barrier between the outside and the inside. Because to pass through that, what do you have to pass through? A very nonpolar section. And if everything's based in water, it's very polar. So what does that polar molecule do when it gets to the surface? Say, hey, that's cool. Then it tries to move through, and it immediately gets pushed right back out. Okay, so we have that barrier now. If we scale up a liposome to a much larger scale, we run into the bilayer sheet, okay, which is ultimately, to a first approximation, what we're seeing with all cells. Okay, that is our cell membrane. Questions about that?
Is that how bile works, or is that different?
I don't know enough about bile to answer that question.
It emulsifies fats.
the impression that I had with bile is that you're looking at a high acid concentration. So what it's potentially doing is breaking down your larger fatty acids, not fatty acids, but the triglycerols into the fatty acids. Once it's in the fatty acid, you can start to do soap things and work with that molecule. But if we look at the triglycerols, those are way too nonpolar that you can't really do much with them and they just pass straight out. So bile tends to be a very high acidity, which helps catalyze the breaking of the triglycerols into the fatty acids. In the fatty acids, we have that polarity available to us now. We can start to move it around. And I'm sure there's more to bile than just that. But water, awesome again. If we take a look at water, it was H2O. That can decompose or separate out into H plus and OH minus. Okay? Well, if we think back to our acid-base definitions, this is where we get the definition for Bronsted-Lowry. So what we're looking at, or one of the definitions for acids and bases, is coming from water. Water, when it dissociates, gives us H plus and OH minus. So if we have a species that gives us H plus, we call it an acid. If we have a species that gives us OH minus, we call it a base. That strict definition between H plus and OH minus is too narrow a definition. Okay, that really only applies to the Arrhenius acid-base definition. Okay. Bronsted-Lowry came through and said, let's ignore the OH minus and look at it more as H plus. H plus is what's moving around, which means our acid definition won't change. It's still donating an H plus. Our base definition changes a little bit. Our base definition is now what is accepting that H plus. Okay? So our acid and base understanding is ultimately coming just from water. Okay? So it's another reason why our water molecules are so interesting. There's this dynamic between the H plus and the OH minus. Okay? If we go through and look at an equilibrium expression, can't remember, did I put this on the next slide? I did, but not enough steps. How do we solve for equilibrium?
Ice chart?
You really want ice charts. I'm not giving you an ice chart. Where do we get equilibriums?
That's what I was solving for.
No, that's solving for the whole thing, kit and caboodle. I want a general expression.
Okay, concentration.
Our equilibrium, if you remember, is capital K for our equilibrium constant, is the concentration of our products over the concentration of our reactants. So if we look at water, we'd be looking at the concentration of H plus times concentration of OH minus divided by the concentration of water, our reactant. That equals capital K, which we said was what? A constant, which means at a given temperature, that value does not change. So what happens if I move into an acidic environment? In an acidic environment, which of those species is highest in concentration? H plus or OH minus? H plus. So if H plus goes up, what necessarily has to happen to the OH minus? It has to go down. So they are inversely related, all back to this K value. What is the K value for water that we're most concerned about? KW, I'll accept that. Okay, so it's the equilibrium constant for water at 25 degrees Celsius. I'm pretty sure that one's right.
Yeah.
Which is 1 times 10 to the minus 14. Which is why if we look at neutral water, where our concentration of H plus and OH minus is the same, the concentration of H plus and OH minus is close, 10 to the minus 7, so that when we multiply the two by each other, we get 10 to the minus 14. Okay. Exponents are a pain to deal with, so what do we develop instead? No, because that's still exponents. pH. Okay. pH is the system we work through, then we don't have to worry about exponents. Which means when we say neutral pH, or sorry, a neutral solution, you tell me pH 7. What does pH 7 mean? It means 10 to the minus 7 concentration of hydrogen ions. Okay. So how do we do that? Well, P is negative log. So if I take the pH, I'm taking the negative log of the concentration of H+. Right? What was the concentration of H+ at neutral pH? Or sorry, at neutral solution? 10 to the minus 7. So the negative log of 10 to the minus 7 is 7. There's our pH scale. Okay? Because everything's done in water, most typically when we look at pHs, we're looking at a scale from 0 to 14. Can we be bigger than 14? Yes. Can we be less than 0? Yes. Okay? To get to those scales, we most typically have to move out of water, because water is largely based off of that balance between those, and it can't really push those extremes. So to get something like concentrated sulfuric acid, if we look at its pH is like -7. Okay? Why? Because we have very minimal water present. Okay? Because the water tends to neutralize and balance out some of that acid concentration. Okay? Where all of this comes from in the mathematics, before we even look at equilibrium, we'd actually be looking at rates. Okay? So if we looked at our reaction, A goes to B, we have the rate of the forward reaction, or the rate constant. We have the rate of the reverse. Okay? If we achieve equilibrium, which is what this is all about, equilibrium, the rates of those reactions are equal. The rate of the forward must equal the rate of the reverse. You can set that into an expression, and you can start to group values. We can group concentrations, and we can group constants. A constant divided by a constant is a constant. We now have a way, or an easier way, to look at our equilibrium. We now have an equilibrium constant that's directly related to our concentrations of our products over our reactants. Right? Did we have to group them in this fashion? Couldn't we have grouped it such that it was reactants over products?
No.
We could have. Mathematically, that is absolutely valid. Why is that not valid when we move into chemistry? Because someone sat down and said, this is how we're doing it, which means, how did you get taught it? That exact same way. So it comes to the definition. For instance, when we look at the molecule of ethanol, right, why do we know ethanol is 2 carbons and an OH? Because of the name, the rules behind the name. Our equilibrium is defined as products over reactants. Right? That does not mean that's how it was in the universe and we just happened to discover that. We set up the rules that mathematically followed, and that's how we continue to use it. Okay? We could have just as easily switched those and come up with a slightly different set of rules that would still get us all the exact same answers and calculations that we want. Okay? You just have to make sure you follow the same rule set. Okay? So we now have a ratio of products to reactants. That's what our equilibrium gives us. And if we go through and look at the equilibrium, we can end up with some big nasty stuff that we don't really want to work with. Okay, we get those exponents. That's where we can move into our pHs when we deal with logs. That gets rid of this exponential value, and in particular a negative exponential value, and turns it into an easy number that we can almost count on our hands with. Okay, because we're in that 0 to 14 range. So we got our definitions for our Bronsted-Lowrys. Nucleophile, electrophile, we can kind of ignore. Okay, at least at this point. When we start talking about the biochemical reactions, we'll come back to that. Okay, so within each of these, we could go through and look at these as Kas or Kbs. The A would stand for acid. The Kb would stand for base. So if we look at the K expression that we've got drawn at the bottom, why is this one for an acid? How do you know you're dealing with an acid? It says H3O+. If we saw OH minus there, we'd be looking at Kb. Okay? So the Ka is ultimately where everything's going to be tied back to. Okay? Actually, I'm not sure I want to go through this. Yeah, we just talked about all that. So we end up now converting any of our expressions into this px value. So that's where it said negative log. So if we wanted the pH, what did we do? We take the negative log of concentration of H+. What if I want the pKa? What do? I take the negative log of the Ka. How do I know what the Ka is? That can be your ice charts. We don't have to worry about that. How do you know what the Ka is? There are tables of Kas given to you that you should be using. Okay? They're either in your textbook given to you on the exam, or sometimes the homework will have you link out to them where they've got tables of Kas. Okay? So you will be using those and manipulating those expressions. Okay? So ultimately, why does biology care about all of this? Okay? So let's take a look at this reaction with acids and bases. Why might biology care about this reaction? Okay, all it is a simple acid-base reaction. Okay, why might biology care? What do we start this lecture with today? Particularly, what about water? Solubility. Does the solubility of the compound change? We move from a compound that is ionic, which is highly soluble in H2O, to a compound that is hydrogen bonding. And while we might predict there is some similarity in hydrogen bonding, so we might see some solubility, is it going to be highly soluble? No. So a simple change in the location of a hydrogen ion within a structure can take a compound from being incredibly soluble to not so soluble. And if we're trying to look at, say, passing things through a membrane, it may start as highly soluble, but if I want it to the other side of the membrane, what might I need to do? Change its solubility into a nonpolar situation so that it can pass through the middle of the membrane, and to get it out the other end, change it back. So I need the reversibility and the playing of the hydrogen ion concentration. Okay. Biology relies heavily on this. Okay. It's so important that we change our understanding, or change the name of it from acid-base chemistry to buffers. And ultimately what's happening with the buffer is trying to control the pH change. Okay? Because if we change the concentration of hydrogen ions too much, we can take a compound from being soluble to insoluble. Well, we take a look at our bloodstream. If our bloodstream changed pH drastically, and now all our blood turned into a solid, would that be a bit of a problem? Okay? So our bodies, or all biochemistry, is designed around buffer systems so that it can control when the hydrogen ion concentration changes. Okay? Because you can see these massive swings. So we need some kind of system to control the concentration of hydrogen ions. Okay? Well, what's going to control the concentration of hydrogen ions? That's going to be largely dependent on the Ka. What acid is actually present? Okay? So our buffer systems are going to be based off of those Kas. And we can switch that around into this expression from Henderson-Hasselbalch, which you may remember a derivation from 152. If you'd like me to derive it after class, I will. Okay? This is an incredibly important equation. It drives pretty much everything that you're going to do in the homework. Okay? It's the relationship between whatever pH you're at, the pKa of whatever acid you're looking at. Okay, how do we know it has to be an acid? It's the A of our acid. So what happens if we give you a nitrogen compound? Nitrogens act as bases. So if you're given the pKa for a nitrogen compound, more often than not, what you're provided would be something along these lines. And they say pKa of this compound. The pKa does not match that structure. The pKa they're giving you is for the acid of our nitrogen compound. You must be very careful with that. It's going to pop up a lot in chapter 3. Okay? Very, very misleading. Okay? But it doesn't matter where you look, that's how they'll reference it. They'll say pKa for an amine is this. No, the pKa for ammonium is this. Anybody know what the pKa for an ammonium is? Ballpark 9. the pKa for an amine, a true amine, is I think 26. Are those significant differences in acid-base characteristics? Those are huge. Okay. pKa of 9 means that that hydrogen can potentially come on and off in a biological system. pKa of 26, we're not touching that hydrogen in a biological system. Okay? It is so basic or so unacidic that we can't actually get a base strong enough in a biological system without destroying the biological system to get that hydrogen off. Okay? So there's our expression, dealing with that Henderson-Hasselbalch equation. Since everybody was talking about it, we got ice charts, everybody's favorite from 152. No. Okay? If you really want to review ice charts, I'm more than happy to pull open a Gen Chem textbook and we can start cranking through some ice charts and buffer calculations and all that fun stuff. You do not need to worry about that at this level. Okay? It's not really necessary because we can kind of cheat and get through everything we need with approximations that are close enough to the truth with our Henderson-Hasselbalch equation. Okay? One of the big interpretations that we're going to come out of, okay, is getting rough ideas. So we can compare the pKa's for any compound out to water. Why compare to water? Our body is in water. Everything we're dealing with is in water. So if I have a pKa lower than water, what does that mean? Is it more acidic or less acidic than water? Be careful, it's more acidic. It's that negative log messing with your head. Okay? So a pKa lower than water, I did write that, yeah, it is more acidic. Okay? If it's larger, then it's less acidic than water. Does it say anything about the base strength? Unfortunately not. Okay? pKa is all about acids, hence the A. Don't evaluate the base strength based off of your pKa. Okay? The other thing we can do is compare it off of the pH. Okay? And your textbook references this. Okay? If a pKa is greater than the pH, then we need to make sure the H is on your structure. Okay? That is because if the pH is very low, what does that mean? We are in a very acidic environment. The hydrogen should be on our structure. If we do the flip, if our pH is very, very high, what does that mean? We're in a basic environment. We should remove the hydrogen from our structure. Okay? Where does that relationship come from? Henderson-Hasselbalch. Which you can go through, and I would kind of recommend you do, at least for a first couple problems, solving out your problem using the Henderson-Hasselbalch equation and looking at those relationships. What do I mean? Come on, where is it? Somewhere back here. pH lower than our pKa. So let's pick a pH that's low. Give me a low pH. 1. Give me a pKa. Okay, 28 is a bit extreme, but I'll accept that. Plus the log of our A minus over our HA. What is A minus? Hydrogens not on the structure. What's HA? Hydrogens on the structure. If we go through and do this math, solve for our concentrations. 1 minus 28 is? Okay, negative 27. How do we get rid of the log? We're going to have to work our... Oh, man. I don't have a nice place to work this. How do we get rid of the log? The anti-log. Nice, that works. Kind of a cheating way to say that statement, but that's true. 10 to the power. Okay, so if we do 10 to the power, we get 10 to the negative 27 equals A minus over HA. Now I'm going to erase all that other junk. What does that mean to us? Is 10 to the minus 27 a big number or a small number? Really, really, really small. What does that mean the relationship is between these two? To get a really, really small number, HA must be massive. Which species should be present? The protonated version or the non-protonated version? Protonated. That's it. If the pH was lower than our pKa, what happens? We jump all the way to our thing, way back down here. Whoops, come back here. Our pH was lower than our pKa. We're in the protonated version, directly out of the Henderson-Hasselbalch equation. Okay. Do you need to use the equation? No. You can cheat and use these expressions. Those expressions are derived from it. It's up to you how you want to manipulate it. I would recommend that you play around with the Henderson-Hasselbalch to see those relationships in those expressions. Okay? You're solving for protonated versus unprotonated, and that can get a bit dicey to manipulate. Done at 9:40? Okay, I'm just guessing that there's nobody outside. This is a question that popped up at ASU. So a former student at ASU sent me this and needed some help with it. Okay. Just because of time, I don't think I really want to talk about it right now, but let's kind of look at it. What they're talking about is how we would make a buffer, which is something that we could do in lab. So we want to prepare 1 liter of 0.1 molar phosphate buffer at pH 7.38 using this potassium phosphate structure and a solution of 1 molar HCl. Okay? So what you have to go through and do is come up with how much of each of these things that you should go through and put together to make this solution. Okay? To do this, we need the Henderson-Hasselbalch equation. pH equals our pKa plus the log of A minus over HA. Anybody already see an issue? Do we have a clear A minus? Okay. Let's say it's this one, because it's a minus. Do we have a clear HA? No, because that one's minus 2. Okay. You will have multiple charges floating through your solutions. You have to be careful in deciding what's A minus and what's HA. Okay. So then the next thing is try and plug and chug some values in here. pH. How many pH values did they give you? 1. That's nice. Okay, our pH value, where is it? 7.38. Our 7.38 needs to equal our pKa plus the log of A minus over HA. Problem that we run into, what's A minus, what's HA? Why is that going to be important? Because that's going to determine which pKa you're looking at. Okay? So which one should we do? Okay. So the one that's closer. So your pKa, you want to be as close as possible to your pH. Because it's already pretty darn close. So we want to be as close as possible. So this pKa is probably going to be our best bet. Okay, the 7.21. Okay, but then what do we have to do to get to a 7.38? Do we have to add acid or add base?
Base.
Why add base?
Make it higher.
Okay. If we went in at just that solution, we're looking at a pH of 7.2. We need to get to 7.38. So we'd have to add base. Why is that a problem? We don't have base. Okay. All we have is acid. So we have to use our pKa2 to solve this. Okay. It's the only way that we can go through and do this. So we use our pKa2 to go through and approximate how we would go through and do this. This then gives us our log. A minus over HA. We need to adjust this. What's HA? What's A minus? It's again tricky. Oops. And that wouldn't be right, because if we looked at our expression for our pKa for this, that puts the wrong species on top. This is pulling off a hydrogen. Okay, so it still doesn't quite work. We'd have to flip that around. And this one was, shoot, just lost all the terms. So we got our PO4, PO4. For HPO4 minus 2 to act as an acid, it would be on the bottom, HPO4 minus 2. This one would be PO4 minus 3. The problem is we aren't going to PO4 minus 3. We're trying to go the other direction. So we end up having to swap these things around yet again and make sure that we got those proper relationships. Okay. Is this a dicey question? Absolutely, because after you go through and do all of this, and you now have the relationship between the concentrations of these. Okay. How do you solve for the concentrations? You have to go through and make the solutions with your grams and all of that. Okay. Big mess of calculations. Okay. What do I expect you to be able to do? I expect you to be able to tell me what the pH is given the concentration of your base species and the concentration of your conjugate acid. Okay. Or be able to determine the pKa. All of that is going to come back to your, which I just deleted, our Henderson-Hasselbalch equation. So if we write this out more generically, A minus over HA. Okay. If I give you A minus concentration and HA concentration and the pKa, can you solve for the pH?
Yes.
Yes. What if I give you the pH and the concentration of A minus and HA?
And you can solve them.
You'd solve for the pKa. Okay. That is the level that I expect you to manipulate. I don't want you dealing with buffer solutions. Okay. The calculations involved in those are way more in depth than you need to worry about. Okay. If you were a true biochemist, you wouldn't even worry about all those calculations because you'd go into lab and you would just titrate it in until you hit the right pH and then move on. Okay. So the extent of those calculations is something that you would find in 152. Do not stress about those in this class. So if you talk to people from other schools, they may very well be going through those details. Okay? They could also be taking a more advanced biochemistry class. Be aware of those limitations within our class. Okay? We will pick up with this on Thursday. But we still have a little bit of time, so I want to kind of look at what we could get from a titration curve. All right, so we've got pH, pKa, log A minus, and HA. And then we've got a titration curve. What can you tell me off this titration curve right away?
There's two equivalent.
There are two equivalence points, which brings up an interesting question. What is an equivalence point? There's the question I want to get at. What does A minus act as? A base. So when you set at the equivalence, the concentration of acid is equal to the concentration of base. Are you saying this base? No. Your equivalence point is saying the concentration of your acid is the same as the concentration of whatever you're titrating in. In this case, I gave milliliters of question mark. What should that question mark be? Base or acid? Base. Why base? How do you know you're adding it to an acid?
Because you're doing a titration.
Where's your starting pH?
It's acidic.
Your starting pH is acidic. And what happens to it? It gets more basic. The only way it can get more basic is if we add base. Okay? I will kind of stop with that. What you're going to be expected to do, and we will do this on Thursday, is going through and labeling your equivalence points. Where do you have HA? Where do you have A minus? Even trickier. It's not HA and A minus. What is it? Two equivalence points means two acidic hydrogens. You have H2A going to HA minus, going to A minus 2. All of those species need to be labeled on this curve. pKa1, the equilibrium for that first step. pKa2, the equilibrium for that second step. Where can you find that information off your curve? Where are the equivalence points? Where's the other term, or what's the other term? You may vaguely remember Form 152, those of you that had it. Equivalence point is pretty meaningless. It's not the equivalence point, it's the half equivalence point. Where are the half equivalence points on the curve? What's important about the half equivalence point? Okay? Believe it or not, all of that information is now available to you, given the equation, our reaction equation, and the Henderson-Hasselbalch. All of that information is on that curve and can be derived off of it relatively painlessly. It takes a little bit of practice getting used to and slowly putting pieces into it. Right? A lot of the sapling homework is based off of this, because an interpretation of a curve is not something that's easily written into a textbook.
Are you going to put it on a test, or are you going to give us those drawings?